So I'm going to build on what Stephen just presented by shifting us outward in the solar system beyond the traditional habitable zone and talk about exploration of the outer solar system and how there's synergies in the science goals for the exoplanet communities as well. So do we have a pointer? Okay. So I'm first going to talk about OPEG, what our goals are, and our and how they connect to the science strategy. Then I'll discuss outer solar system exploration, what we've done in the past, and where we are hoping to go in the future, and specifically talk about science goals for the giant planets for ocean worlds, so going beyond the traditional habitable zone to a possible other habitable zone that doesn't depend on surface water. And I'll end with talking about IO and extreme tidal heating. So these are all areas where we have observations and we hope to have future observations that could really connect to exoplanet characterization. So the Outer Planet Assessment Group is not an advisory group. We are an assessment group. We get together with the community and we assess what the community's perspectives are on outer solar system exploration. And then we serve as a form of communication to NASA on behalf of the community. I have a list up here of all of our members, and the organizing committee members are Lene Quick, Abby Reimer, and myself for this meeting. So we've really had a lot of fun working with the VexEgg team and the ExoPig team on this. We recently had a homework assignment from the Planetary Division Director, Lori Glaze, for all of the assessment groups. She asked us to poll our communities and figure out what our top science goals are for our community in advance of going into the Planetary Science Decadal Survey. And this was a really interesting exercise because we got this broad community of outer planet researchers together and discussed where we want to go and what questions we want to answer over the next 10 years. And we came up with 3 top questions because we were asked to give 3 questions. And they were, what is the origin, structure, and evolution of planetary systems? What present-day processes shape planetary systems? And how do these processes create diverse outcomes across different worlds? And then finally, what is the history and distribution of life in the solar system? Now, we're not very good at our homework because we put in a 4th question, whether we were asked to or not. But we wanted to know, how can exploring the outer solar system and exploring the solar system help to advance exoplanets, Earth science, and heliophysics? How can we connect across divisions and break down those pipelines? Well, if you take the Exoplanet Science Strategy Goals, which was a National Academy study, they identified 2 primary goals with a lot of sub-goals under them. And they are the formation and evolution of planetary systems and the property of exoplanets and the potential for habitability. And there are a lot of great connections between what we want to explore in the outer solar system and what exoplanet scientists want to learn about exoplanets. So there's a good connection between the 2 communities, just like with the inner solar system. So outer solar system exploration has benefited from numerous spacecraft. We've had spacecraft fly by planets in the outer solar system, and we've had spacecraft orbiting planets in the outer solar system. We've had flybys of all 4 of the giant planets, multiple in a couple of cases. With Jupiter and Saturn, we've had spacecraft orbiting, and we've learned a lot about the system science from those. The moons of the giant planets are particularly interesting because several of them may have subsurface oceans, and that makes them potential places for life, and they're a big focus for us now. And that includes Titan, which also has a thick atmosphere, so it's very interesting on multiple levels. And in the future, we have several options or possibilities of places where we could end up sending spacecraft. And it's important at this stage that we start talking with exoplanet scientists and start involving exoplanet experts in planning these missions so that we can make observations that can feed into characterization of exoplanets. So this is a good time for the communities to start getting together as missions are selected and move forward to the outer solar system and looking at how we can work together. So moving on to the science of the outer solar system. There are many questions about the giant planets that we have answered and that we are trying to understand. We have the Juno mission currently orbiting Jupiter, and that has provided an amazing discovery about the interior structure of Jupiter. we originally thought that each of the giant planets has a solid core with a solid boundary around the next between that and the layer above it. But the Juno observations through gravity measurements in orbit around Jupiter have found that the core doesn't have a strict boundary between itself and the outer layer. It's actually a fuzzy core that is diffusing into the outer layer, and there's an exchange between the core and the outer layers. And there's a question, is Saturn similar as well? Maybe we can learn something more from the Cassini proximal orbits. You get out to the outer solar system, and we really have a lot of questions about the interior structure of the ice giants because they are very different from Jupiter and Saturn. So we can't really just take what we know about Jupiter and Saturn and apply it and assume that we understand the ice giants. We need to send a spacecraft, preferably an orbiter, to really start understanding the interior structure of these two planets, which are in a class, a mass class, similar to many exoplanets that have been discovered. There are at least 4 posters that talk about interior structure, that provide science results that are relevant to the interior structure, and I apologize if I missed anybody's posters, but I tried to go through all the abstracts and find everything relevant. Now, giant planet atmospheres, the outer layer of the giant planet is the atmosphere where photochemistry takes place. You have clouds forming, you have some haze production, and each of the giant planets has differences in its composition and its temperature structure. And I'm not going to go into a lot of detail on this because we have a talk tomorrow by Julie Moses, who is going to discuss studies of photochemistry in the giant planets in our own solar system and how that is relevant and how she's been able to use that to study exoplanet chemistry. Finally, the giant planet atmospheres are very dynamic. There's a lot of processes with cloud formation. There are storms that occur. And so you can't just observe a giant planet and think that you understand how it looks. A really good example is the Cassini mission, which orbited for many years around Saturn, and in 2010 found this storm that was starting to form, and over several months watched this storm start to spread out across the surface or the atmosphere of Saturn. And it was really interesting to study that and get a better idea for these types of processes in the giant planet. The Hubble Space Telescope has been very valuable for studying the giant planets and observing different phenomenons in the weather systems on Uranus and Neptune as well. So this is something that is ongoing work, and we try to understand these processes on the giant planets. But when you think about clouds in planetary atmospheres, they're not constant. There's a lot of dynamics and changes throughout time. And my final slide on the giant planets is we want to know how they formed. And the best way, or one of the best ways for trying to understand how giant planets formed, is looking at the composition, the elemental composition of their envelopes. The only planet that we have the best measurements for is Jupiter, because we sent the Galileo probe into the atmosphere and we were able to get bulk composition of not just carbon, nitrogen, oxygen, sulfur, and phosphorus, but we got the noble gases, and the noble gases are really important for helping to understand the heavy element composition, frequently referred to as metallicity for the giant planets. In the planetary science community, we use metallicity less than that. But what is interesting about this, there's 2 different theories for the formation of the giant planets that are leading theories. One is that solid material built up a core that reached a point where the mass of the core was enough to accrete a large atmosphere through runaway accretion. The other theory for the formation of the giant planets is that clumps formed in the disk as the planets were forming, and then the disk collapsed and formed a planet. The disk collapse theory is much faster than core accretion. And looking at the bulk composition of the atmosphere can help you sort of to try and tell the difference between the 2 of them, if you can also take into account how the planets changed since formation. So for Jupiter, we see that the composition of the heavy elements relative to hydrogen compared to the protosolar nebula's composition, there is an enrichment of about a factor of 2 to 4 in all of these heavy elements except for oxygen, helium, and neon. which suggests that either the protosolar nebula where Jupiter formed was enriched in the heavy elements across the board, or the solid material that formed Jupiter had similar enrichment in all of the heavy elements relative to each other. Now, oxygen was depleted because it's thought that the Galileo probe went into a dry patch in Jupiter's atmosphere, so that Juno has been working to try and get a bulk composition of oxygen. And then helium and neon are removed into the interior through processes that cause it to rain out into the interior. So they're depleted in the envelope for other reasons not related to the formation. Now, moving outward in the solar system, we have a lot fewer measurements, but we have a carbon measurement for each of the giant planets. And when you look at the carbon measurement in Saturn compared to remote sensing observations of the carbon measurement or the nitrogen measurement in Saturn's atmosphere, it looks like Saturn is different from Jupiter. So the formation process may have been different, or the solid material that went into forming Saturn may have been different. Now, the problem here is that the error bars on this measurement are huge, and it is remote sensing, so a probe into the atmosphere of Saturn would be really valuable. Additionally, if we could get the heavy noble gases and see if they trend in the same way as carbon, or if they are different, that would help us to have a better understanding of the formation of Saturn. Moving even further outward, we have a lot more uncertainty. We have measurements of carbon in the ice giants, and then we have a detection of sulfur in the atmosphere, which can give us an estimate of the upper limit of nitrogen if nitrogen is not being removed into the core like helium and neon in Jupiter's atmosphere. So it's possible that the ice giants are also very different from Jupiter, maybe similar to Saturn. There's a lot more that we need to understand, and measuring the noble gases again will help us to understand these formation processes. Now, the final thing that I have on this plot are two potential analogs for the solid building blocks that would have formed the giant planets, and that is chondrites, which would be rocky material, an analog for rocky material, and then the one comet for which we have noble gas measurements, and they're shown here, and that's 67P Trium of Gerasimenko, which was studied by the Rosetta spacecraft. And as you can see, these are clearly not the building blocks that went into Jupiter, because the trend in the noble gases and the trend in the heavy elements are very different from Jupiter. So that comet is not a very good analog for icy material that would have formed Jupiter. It may be a good analog for the ice giants, and it may be a good analog for Saturn. We need more information to know, though. The giant planet systems are very fascinating as well. These are little planetary systems with moons and rings in orbit around them. And we've really gotten a wonderful understanding of Jupiter and Saturn through the spacecraft that have orbited them. They've studied the rings, they've discovered many moons. We've looked at the moons that are larger and that experience a lot of tidal heating and found subsurface oceans in them. And we've learned quite a bit, but most of what we know about Uranus and Neptune is from the single Voyager flyby. We do have Hubble and ground-based observations, but those are very limited. So we'd like to learn more about the rings and the satellites of the ice giants. Additionally, the magnetospheres of all four of the giant planets and compared to Earth are very interesting as well. Uranus and Neptune in particular are just plain weird. They seem to be offset from the core. Uranus is tilted in a strange way so that sometimes you've got the solar wind coming down on the pole, sometimes it's on the side. And there are so many questions about how these two magnetospheres work that we really need an orbiting spacecraft to be able to understand. Moving on to the moons of the giant planets, and one of the biggest topics and hot, interesting areas for outer planets is the ocean worlds, the icy moons, that may also be a place for life underneath an icy core. So we have Titan, we have Europa, we have Enceladus, possibly Triton, and we're interested in exploring these bodies to see if life exists underneath these cores. So there's two talks that we'll be talking about the icy moons, and then we've got two posters. And I hope I didn't miss anybody. I think I am missing a poster on Titan here. So check out the posters and the talks if you want to learn more about the icy moons. Three icy moons are of particular interest to us because they have plumes. And in Enceladus, I believe the most recent results by Cassini are suggesting that these plumes are endogenic, which means that material from the ocean may be spewing out into the magnetosphere and accessible, where we can take measurements of the composition or material from the interior oceans and start looking for biomarkers. Europa had plumes that were detected by the Hubble Space Telescope, so that synergy between the astrophysics and planetary communities is really important. And they were confirmed when people look back at the Galileo data and noticed observations with the magnetometer that we actually passed through these plumes with the Galileo spacecraft. These plumes may be endogenic. We don't know. We're hoping that the Europa Clipper mission will be able to teach us more about that. And then finally, Triton was, I believe, the first outer planet's moon where we observed plumes. And that was Voyager, which observed these plumes from the subsurface. They were close to the subsolar point, and at the time, these plumes were interpreted to be driven by solar heating of the nitrogen ices, causing plumes to come up. But the discovery of these other plumes made us start revisiting that question. Is it possible that Triton also has a subsurface ocean and maybe these plumes are endogenic? It's worth going back to explore and try to understand the source of these plumes. And the final topic for the outer solar system is Io. Io is the most volcanically active body in the solar system, and this is because it is subjected to extreme tidal heating. And it is a good analog for inner exoplanets that also experience extreme tidal heating, so we can understand the processes to which these planets are subjected to. And I'm not going to talk much more about it because there is a talk later today and a poster about Io. And finally, just want to talk about strategies for our communities. It's good for us to get together with meetings like this. I'm hoping that we can have more programs that are funded for cross-divisional work. And I led a white paper that went into the astrophysics decadal survey that I plan to submit to the planetary and heliophysics decadal survey. So if you're interested in co-signing this, then let me know. And pass it on to Vicki now.